Hello everyone. Today, let's talk about this topic, making it comfortable, running water, temperature control, and sun protection. This is the course Introduction to Geochemistry. Today, we would like to talk about our climate. We want to talk about the substance that is needed to make the climate habitable. Our climate is stable. Why is that a surprise? So we know that from the early stage of the solar system to it is now today, the solar luminosity has changed over time. And the climate condition on other planets of the solar system is harsh, except the Earth. To make our climate stable and comfortable, it requires both liquid water and solid rock at the surface. Why is that? This is something we want to figure out in today's class. We want to first talk about the Earth's volatile budget. Volatiles, what are they? Generally, when we talk about volatile, we actually refer to water, CO2, nitrogen, oxygen, and methane, and other gaseous substance. So what is regulating their abundance in the atmosphere and ocean? I would like to cite a paragraph in James Lovelock's book, Gaia Hypothesis. So I like this book a lot, but I think today it's somehow difficult to find the Chinese version of this book, 盖亚大地之母. I will highly recommend you to read this book. So in this book, he wrote, "The only feasible explanation of the Earth's highly improbable atmosphere was that it was being manipulated on a day-to-day basis from the surface, and that the manipulator was life itself. The gas composition in our atmosphere is highly improbable based on chemical reactions. So there must be other things that keeps it away from equilibrium. So our atmosphere is actually at a highly disequilibrated status." We know that the volatiles, they are important for maintaining our climate. That's the reason we care so much about the green gases. So volatiles are important. Where did the volatiles come from? So let's take a look at some numbers. The volatile content in Earth's silicate, that means our crust and mantle, is about 700 ppm of water and 200 ppm of CO2. You might ask, what? Do we have water and CO2 in a rock? Here you need to be aware that we are actually talking about crystal water. For example, for some mineral, you will see crystal water in its formula, and sometimes you also see OH in the chemical formula. This is actually how water exists in rock. And for CO2, we are actually talking about, for example, carbonate. They are petrified CO2 in rock. The Earth silicate is actually quite depleted in volatile compared to the solar nebula, because we know in the solar nebula, the major component is hydrogen and helium, and both are volatiles. So of course, compared to these gaseous components, our Earth is very depleted in volatile. But the water CO2 ratio, which is 3.5 in our silicate, is higher than the ratio in chondrite, which is less than 1.5. You might think, where did the water come from? Here, I would like to ask you a question. Please recall the lecture regarding our planetary system. So we have several visitors from the asteroid belt or Kuiper belt or Oort cloud. Among Earth's visitors, who has the highest volatile content? Can anyone tell me this? So the answer is comet. Because most comets originate from the Oort cloud, and the Oort cloud is at the most distant place of the solar system. It is far beyond the snow line we have talked about. So comets have the highest volatile contents. How do the volatiles distribute on Earth? there is 100 times enrichment in the combined atmosphere, ocean, and crust. That means the surface Earth. Water constitutes 7.2%, and CO2 constitutes 1.5%. This number means the weight proportion in surface Earth. That is actually a lot. And despite the massive degassing during Earth's early history, there is still substantial water and CO2 in Earth's interior. We know that because based on the composition of volcanic gas. Why is that? Why we still have so much water and CO2 in volcanic gas? Why? So these are the topics we want to address. To address these topics, we need to first talk about the volatile budget. In my previous lecture, I have said that the Earth's mass is not large. Therefore, it has lost many of the original gases accreted into Earth. There is a loss flux of gas to the space. What are the mechanisms that cause loss of volatiles to the space? There are several possibilities. The first possibility is thermal escape. Individual atoms or molecules, they can escape a planet when their velocity is high enough. This is the principle why we can send satellite to the space and make it orbit around the Earth, because we give it a escape velocity. For individual atoms or molecules, below are the controlling factors that control their velocity. The first is the temperature. The second is the gravitational field of the planet, and this is determined by the mass of the planet. The third is the mass of the molecules. The smaller the molecule is, the more likely it will escape to the outer space. And the mass is massive to prevent thermal escape of most gases except hydrogen and helium. I have mentioned in my previous lecture, hydrogen is rare on Earth and also helium is rare on Earth. And the second is solar wind. Particles of the solar wind has very high velocities. So we know that the solar wind is not just wind. It actually has particles inside it. And the particles that can strip gases from the outer atmosphere. What are the controlling factors for this process? The factors include the distance to the sun and the presence and size of a liquid iron core. Why? Because the liquid iron core is the source of the magnetism of the Earth. And Earth has the largest magnetic field of any terrestrial planet in the solar system. The good thing of that is it provides protection of Earth's atmosphere and life. This is an artist's view of how the Earth's magnetic field protects the Earth from the solar wind. The sun is constantly emitting particles to the surroundings, and the magnetic fields around the Earth can help to protect the attack from these particles and help us to maintain our volatiles. Therefore, we would like to come up with some quantitative estimate of the loss flux of gas. We want to know the loss flux of different gaseous species like maybe helium or water or CO2. And to do that, we can use the so-called residence time approach. So how to do that? So we know the gaseous species, they are mainly present in the atmosphere. Based on the volume of the atmosphere and also the concentration of this gas in the atmosphere, we can calculate the stock of this gas in the Earth's atmosphere. And then we also know the production rate within the Earth, especially helium. Helium-4 on Earth is not from the solar nebula. Those helium-4 coming from solar nebula is long time ago gone, because our Earth is not mass enough to keep this gas. So the helium-4 you see today, it is produced from rock. In rock, we have these radioactive nuclei, uranium and thorium, and these will undergo some radioactive decay to form lead and helium. So you see the production of helium is quite substantial. Here I have a question. What is the name of this radioactive decay? So the answer is alpha decay. I hope you still remember from our lecture regarding the chart of nuclide. Based on the mass of the rock on Earth and also the concentration of uranium, these nuclides in the rock, also based on the decay rate constant, we can calculate the production rate of helium. We know the stock, we know the production rate. With the assumption that the system is at a steady state, we can estimate the escape flux of helium-4 from the top of the atmosphere to the space. With this flux of helium-4 and with further calculation, we can also estimate the loss of water and CO2 to space. And we can also estimate the residence time of helium. It is 10 to the 6 years in the atmosphere. And we also, based on this calculation, we know that the loss rate of water and CO2 is very low. It's almost negligible. Here, I would like to say a few words about residence time approach, because this is a very common approach in this department for people who study marine chemistry. So usually when we talk about residence time, we need the assumption of a steady state. What is the definition of a steady state? Here I have a water tank, and the water tank is receiving an influx of 10 liters per hour. After 3 hours, its volume will change from 70 to 100. Is the system at a steady state? Probably not, right? And how about this? Now I have another tank with a volume of 100, and it's draining at this flux. After 3 hours, its volume will decrease to 70. Again, is this system at a steady state? Probably also not. So how do you define a steady state? This would be the case of a steady state. This water tank has an influx of 10 liters per hour, and it also has an outflux of 10 liters per hour. So with the same influx and outflux, after 3 hours, you will see this. The volume is still 100 liters. Does it mean the water didn't change during the 3 hours? No. In fact, it is constantly changing, right? However, because this rate here, they are the same, so it looks like the volume didn't change. Let's take another example. Today, my weight is 100 kilograms. Tomorrow, I measure my weight again. It is also 100 kilograms. Does it mean that I neither eat nor poo? Of course, I eat, I also pee and poo. But my mass won't change because my mass is at a steady state. Whose mass is not at a steady state? The child who is growing fast. You might find that their mass is increasing rapidly. That means they are not at a steady state. But for most adults, their mass, their body weight, is at a steady state. What is the other possibility that you do not see changes over time? Like you don't see a change in weight over time. What would be the other possibility? This is the other possibility. Basically, no influx and no outflux. If I am made as a mummy, then my body weight won't change. So if you see the mass or the volume doesn't change, it could be either there are constant in and outflux, or there is simply no flux. But for natural systems, most of them will be in this case, not this case. How does the concept of steady state lead us to the concept of residence time? This is the definition of residence time. The average length of time a molecule stays in the pool. How can we calculate the residence time of water in our example? So there's an equation for this. You need to divide the total mass or volume in the pool by the rate of supply or removal. Should you divide by this 10, or 20? The answer is you divide it by this or this, not 20. Because the flux here, they are the same. So you only need to choose one of them. And so 100 divided by 10 is 10 hours. So the residence time of water molecules in this tank is 10 hours. So this is our case where we want to calculate the residence time. We have the stock of helium in the atmosphere, and we also know the production flux by rock. Based on the assumption of steady state, the outflux here should be the same as the influx. We can use the stock and the flux to calculate the residence time. So this is the residence time. The residence time of helium-4 in our atmosphere is 10 to the 6 years. This is not long. Then, based on additional calculation, scientists were able to calculate the loss rate of water and CO2 into the space, and they figure out that the loss rate is very low, almost negligible. This is because these two molecules, they have a higher mass compared to helium-4. And here I would like to say a few words regarding the residence time because it is a very useful concept in marine chemistry. Below are a few examples. If you know a system, it is at a steady state, or you assume it to be a steady state, and you know there are sources of input, and you also know the rate of the input. Then the rate of input can serve as a guideline for you to search for sources and rates of output. That's exactly what we did in the helium-4 case. We know the stock, we know the input flux, we then should also know the output flux. If the output flux that you know is not large enough to match your input flux, that usually means some other output flux is missing. So you need to look for that output flux, and then you can also estimate its rate. That's how we use the residence time approach. Another application is if you know the residence time of a solute. Solute means the component dissolved in solvent. You can compare it with the residence time of solvent to know if the solute can be distributed evenly in the system. The solute and the solvent may have different source. For seawater, the water may come from rainwater or river water or a melted glacier. It has several sources, and each of these sources, they have different, for example, sodium concentration. Rainwater has very little sodium concentration. River water may have slightly higher sodium concentration. Therefore, if you want to know whether sodium can have relatively even distribution in the whole ocean, you can compare the residence time of sodium to that of seawater. Now, my question is, which of the following case would infer that the solute has a relatively even distribution in seawater? The first is the residence time of solute is longer than that of the solvent. The second is the residence time of the solute is shorter than that of the solvent. Which one? My answer is the residence time of the solute should be longer than the residence time of the solvent, because in this case, the solute can stay in the system after being flushed by the constantly changing solvent for several rounds. After several rounds, the solute should have more homogeneous or even distribution in the system. And the third process that may lead to the loss of our volatiles is by UV light. If water molecules reach the upper atmosphere, the solar UV light converts them to hydrogen atom, which escape very easily. So the controlling factor is the probability of water to reach the upper atmosphere. The good news is the Earth's atmosphere has a water trap that keeps most of the water in the lower atmosphere. So let's look at the thermal structure of our atmosphere. This is temperature, and this is the height above the ground. So we live here, the troposphere. This is the temperature we know, around something like 15, 20, 25, depending on the latitude. However, with increasing height at the tropopause, you can see that the temperature decrease rapidly. 273 is around the 0 degrees Celsius. So the temperature here is actually below the freezing point. Therefore, water will become crystal at this point. And when this happens, it's less likely for the water to escape into the space. That's the reason why the authors of our textbook think this is a water trap. And here I would like to say a few words about UV light. We talk about UV light when we talk about the planetary system. The irradiation of UV light on stellar dust is one of the important mechanisms to create molecules. So UV light can result in the formation of molecules, but it can also result in the breakup of molecules. And in this case, here, UV light results in the breakup of water molecules. I don't know how many of you are aware of the power of UV light. I know that you will probably put some lotion on your skin in summer to protect it against the UV radiation. And when you go out on the street, you will see some commercial boards on the streets. The color is almost fainted. This is because of the UV light. And previously in my lab, one of my students, his master thesis project works with UV light. So I have a very strong impression regarding the power of UV light. Do you know when you irradiate a bottle of seawater with UV light, what will happen? The answer is the water will turn yellowish. Why? Because UV light will convert the chloride ion dissolved in water into chlorine gas, which is toxic. And when you see seawater with this astringent smell, it's like, oh my God. So you see, UV light is really powerful. It breaks up water, and it also combines chloride ions into chlorine gas. Below is what we also know. First, based on geological records, scientists believe that the pool size of water in the ocean is relatively constant. But we know less about CO2. We don't know whether the DIC concentration in seawater has been constant over time. But we do know that the water volume in seawater is almost constant over time. And we also know that the loss rate of water and CO2 to the space is negligible because we have roughly shown the calculation here. This is the loss rate. And we also know that even today, the volcanisms and hydrothermal activities, they continue to supply water and CO2 to the surface Earth. So we have supply, we have negligible loss, but we have constant stock. Recall the residence time approach. In order to balance the budget, there must be other laws that we have not considered so far. So the scientists infer that the major removal mechanism of water and CO2 from the surface Earth is to the lithosphere by subduction. We will talk more about this in our lecture regarding hydrothermal system. Therefore, this is what scientists believe. The majority of water is in solid Earth. These are the numbers water mass scientists have estimated for the Earth. We know that the ocean is the largest pool of water. This is the number here. We also know that ice cap is another large pool of water, but we have less fresh water. And please look at the solid Earth. The number here is almost the same as the number here. That's phenomenal. The water here, please do not think of this as liquid water. So the water exists in the form of crystal water or in the form of OH in the chemical formula of minerals. Scientists conclude there is another ocean hidden in the solid Earth. That's the first important message of the lecture today. Let's continue with the second part of this lecture, evidence of liquid water in Earth's early history. How do we know that there has been water in the ancient Earth? What is the evidence that supports this argument? One of the most important evidence is certain types of rocks or minerals. Their presence will indicate there was water because their formation involves water. What are they? We will talk about them later. These would only tell us that there is water, but we need some dating technique in order to know that what was the earliest time that there was water. For that, we need to do radioactive dating. And here, I would use the chance to introduce a very specific dating technique that involves zircon geochemistry. So we will talk about its radioisotope geochemistry, its chemical composition, and its stable isotope geochemistry. We will show you why zircon is widely used in geoscience and how it helped to prove the presence of liquid water in Earth's early history. Here are the types of rocks or minerals that would imply the presence of water. Sedimentary rocks, limestone. Limestone was carbonate, and carbonate its formation involves liquid water. And chert. Chert is produced from SiO2. Its formation also involves water. These are not surprising because they are all within the category of sedimentary rocks. However, for the following, you might be surprising. Granite. The presence of granite would imply there is water. Why? Because granitic magma is produced by hydrosmelting of basalt. We will talk more about this when we talk about the geochemistry of subduction zone. And zircon, because zircon is ubiquitous in hydrous granitic rocks. Today, we will focus on this part. Zircon, this is its chemical formula. It is a silicate mineral. Zircon is so beloved by geoscientists. Why? Below are the special things about zircon. It is one of the highest temperature and most stable minerals found in rocks. That means because they are high temperature mineral, they are resistant to melting event. And we already talked about this in the course of radioactive dating. If a mineral or a rock is melted, then it becomes an open system again, and this will reset its age. Therefore, if we want to know the oldest possible age, we would like that the mineral after it is formed is not open to the environment again, because zircon is the most stable high temperature mineral that you can find in rock. So that usually means they are resistant to melting events. That's here. Zircon are so robust that they often survive multiple melting events. It has low abundance, but very common in rocks. If you search them harder, you can find them. All granites and sandstone contain some grains of zircon, so you can actually find zircon in sea sand. And zircon grams can be individually dated. That's good, right? Because for other isochrome, you often need different minerals. But for zircon grams, you can only focus on them. You don't need to look for another mineral grams. So you don't need multiple grams for isochromes. Zircon offers multiple ways of radiometric dating. Another good thing about zircon when we want to use it for radioactive dating is zircon concentrates uranium and includes lead during crystallization. Recall the course of radioactive dating technique, we would prefer a system where we know that the daughter nuclide is 0 at the beginning. For zircon, this situation will stand because during crystallization, it will exclude lead, which is the product of these uranium-lead isotope pairs. Zircon also supports uranium-thorium or uranium-helium dating. Furthermore, it can be used for fission track dating. So with these zircon grams, you can do multiple datings. Isn't that good? That's what scientists would do. They would measure their lead-207 to uranium-235 or lead-206 to uranium-238. These are two independent isotope pairs. The principle here is this ratio, uranium-235 to uranium-238, this ratio is well known for Earth material, and this ratio is assumed to be constant in nature. This isotope pair, the y-axis, has a half-life of 4.5 billion years, and this isotope pair at the x-axis has a shorter half-life of 0.7 billion years. They are independent methods. With this zircon, you can do two methods. The best thing is you can do these two methods on the same sample. When the age from the two methods agree, it is robust and concordant. If the data plot perfectly on this line, so this line is a calculated line based on the assumption that this zircon grain follow this decay, and the zircon grain is not affected by other external nuclides, then your dating data should fall on this line. So this line is the line of Concordia. And now I'm going to talk about the fission check. So fission check dating is quite often used in geoscience department. We talk about nuclide fission when we talk about the chart of nuclide. During nuclide fission, the split of the nuclide will create some track. It will damage the crystal structure. This is the initial structure. When nuclear fission occurs, the nuclides will damage the crystal. So under specific microscope, you can see this damage. And the number of track will increase over time. So fission track is the product of spontaneous fission decay. It is not alpha decay. And uranium-238 is the only isotope with a decay rate. Here it means spontaneous fission decay. That is relevant to the production of fission tracks. By counting the number of tracks, you can obtain the age of this crystal. The applicability is 0.1 to 2,000 million years. I will not talk too much about the detail here. You only need to know that you can also do fission check with zircon. This is a famous area called the Jack Hill Formation in Australia. You see this reddish rock. They are sandstone. And this is Jack Hills in Western Australia. In this sandstone, I already mentioned you can find zircon in sand. Of course, you can also find zircon in sandstone. Here, they pick the zircon grams in sandstone and perform dating. And they found that the oldest date they can get from the zircons of Jack Hill Formation is 4.4 billion years ago. So how old was the age of the solar system based on the dating of chondrite? About 4.5, 4.6 billion years. So this is very old. So if you consider the uncertainty of the dating technique, this age is probably the same as the age of the solar system. However, the oldest sedimentary rock, the Jack Hill Formation, date 3.9 billion years ago. That is about 0.5 billion years younger. And the zircons are up to 0.5 billion years older. So zircons are older than its surrounding rock. What kind of sense does this make? So scientists think the most reasonable explanation for this phenomena is the zircon was produced elsewhere, was weathered out, and then later deposited together with other sand grains to form the sandstone here. So the sandstone will be younger, while the zircon will be older because it was originally in other rock, probably granite. And why zircons imply liquid water 4.4 billion years ago? Because zircons, they are rare in anhydrous mafic rocks. So please recall the Bowen series. We talk about different volcanic magma. We have ultramafic rock, and felsic rock. When we talk about mafic rock, it usually refers to basalt. And basalt is anhydrous. It means it has very low water content. But Zircons are common in hydrous granitic rocks. That means granite. And here we have another geochemical evidence that support that the zircon found in the Jack Hill Formation is from granite. Zircon has a charge of 4+. Therefore, titanium can substitute zircon. Please recall isomorphic substitution. The amount of isomorphic substitution is dependent on temperature. It is a rock thermometer. It measures the temperature at which the zircon was formed. And the Jack Hill zircons have titanium contents suggesting a source magma of 750 degrees Celsius. This temperature is consistent with the temperature we know for felsic magma. Felsic means the magma for granite, 650 to 750 degrees Celsius. In contrast, if it's mafic magma, the magma that produces basalt, then the magma is anhydrous and the temperature is usually higher than 950 degrees Celsius. Therefore, the trace metal geochemistry of zircon support the hypothesis that the zircon originated from granite, and granite implies the presence of liquid water. And lastly, we will talk about stable isotope evidence. We talk about this because in this department, we use stable isotope a lot. So what are stable isotopes? By definition, from our lecture about chart of nuclides, we know that stable isotope does not undergo radioactive decay. Here, I have a spatial periodic table where we have this classical stable isotope geochemistry that generally involve hydrogen, carbon, nitrogen, oxygen, and sulfur. In this department, several of the faculty members, we work with this isotope. Like I work mostly with carbon isotope and sometimes with nitrogen isotope. Yongbing works with hydrogen isotope and oxygen isotope. And there are also other isotopes that other scientists around the world they work with, like a lithium, beryllium, magnesium, iron, boron, silica, chloride, chlorine, and helium. So this is to give you an overview because not all the elements here, not all of them have stable isotope geochemistry, so mostly just here. What are the oxygen isotopes that we usually work with? They are oxygen-16, it constitutes 99.7%, oxygen-17, 380 ppm, and oxygen-18, 0.25%. In general, these three isotopes, they behave similarly in physical and chemical reactions. They all participate in physical and chemical reactions, but with different kinetics. That means they have different reaction rates. What is the main parameter or factor that determines its rate? Temperature. So you see temperature affects many things. Previously, we talked about titanium substitution of zircon. It is also temperature dependent. And here, this is also temperature dependent. And the same, if you think about foraminifera, you talk about the geothermometer for past seawater temperature. You usually use oxygen isotope or magnesium-calcium ratio. When you use magnesium-calcium ratio, you are basically using the idea of isomorphic substitution. And isomorphic substitution is often temperature dependent. And here, when you use the oxygen isotope as a geothermometer, you apply the principle here. Oxygen-16, because it is lighter, it will evaporate a little bit more easily than oxygen-18. We call this stable isotope fractionation. Because of these effects, the oxygen-18 to 16 ratio in water vapor is about 0.9%. That means 9 per mil, lighter than liquids at 25 degrees. So if I have water here, the oxygen isotope value here will be slightly heavier than the isotope value here. This is because of isotope fractionation. The level of fractionation is dependent on temperature. And when we report stable isotopic value, we usually use the delta notation. So this is the definition. So we have the isotopy ratio. This is mole to mole. This is also mole to mole. So we have the measured isotopy ratio 018 to 016 of our sample. And we calculate the difference in ratio between our sample and a standard. And for oxygen isotope, our standard is standard mean ocean water. This is when you measure water. And if you measure carbonate, for example, foraminifera, you use PD belanite. You first calculate the difference in ratio, and then you calculate the relative difference by dividing the difference to the ratio of the standard. And because the difference, the value here, is usually very small, like 0.99901 or 1.00008. Because the difference is so small, we will multiply by 1,000 to enlarge the difference, to make the difference more readable. So that's the reason why we use the unit per mil. So important concept. Stable isotope fractionation is strongly temperature dependent. What kind of temperature condition will result in stronger fractionation? Higher temperature or lower temperature? The answer is low temperature. Because at high temperature, no matter it's 018, 16, all molecules move quickly. Therefore, at high temperature, like more than 1,000 degrees, there's no fractionation. If you want to get fractionation of 0 per mil, which is significant fractionation, you need temperature lower than 100 degrees Celsius. The water cycle fractionates oxygen isotope because the water cycle on Earth is basically low temperature reaction, while the igneous process that produce igneous rock, it barely fractionates oxygen isotope because they are high temperature processes. So for the ocean, we start with a delta 018 of 0 per mil. When we have 0 per mil here, the vapor above the ocean would be as low as minus 13 per mil. When the vapor moves toward the land, and when it encounters mountain, it will produce rain. And rain is liquid water. And in liquid water, the heavier isotope will be relatively enriched. Therefore, the rain here is heavier than the vapor here. It is minus 3 per mil. And because the heavy isotope is selectively precipitated, the remaining vapor will become increasingly more negative. And next time, the next rain in this mountain will be even more negative than the rain in the first mountain. And we want to talk about mineral-water interaction. Now we focus on water. So we want to know how this mineral-water interaction would affect its isotopic value. Minerals that formed in contact with meteoric water should have isotopic composition affected by meteoric water. For orthogenic minerals, that means those formed in sedimentary environments, their isotopic value will plot on subparallel lines to the meteoric water line with enrichment in 018 relative to meteoric water. So that means this. When we talk about meteoric water line, we actually refer to delta 018 in the x-axis and delta D. Delta D means delta 2H. We can also measure the hydrogen isotope of water. And scientists figure out that globally or locally, if you measure the rainwater, you will find that the rainwater will plot on this line. That means the 018 and H2, they will fractionate proportionally. As a result, the rainwater sample you collected in different parts of this region, they will have a relationship. And for standard mean ocean water, by definition, it will plot at 0. Freshwater or rainwater will be more depleted in 018 and delta D. And for minerals that undergoes mineral-water interaction, their 018 will be more positive. The square here is kaolinite. We know kaolinite is clay mineral. And all clay minerals, they are involved in a water cycle. And you see they also plot parallel to the meteoric line. And halloysite, another clay mineral, is also here. And with this graph, I want to give you an overview what kind of stable oxygen isotope value you will find. Standard mean ocean water by definition is around 0. For anhydrous basaltic rock, its isotopic value is around 5 to 9. With increasing interaction with water cycle, granitic rock is already hydrous. Its value will be slightly more enriched. When it's sedimentary rocks, it will be even more enriched. So having this background information, we come back to zircon. So zircon, though relatively stable compared to other minerals, is a high temperature mineral and it's a stable mineral, but it can still undergo some interaction with water. So let's look at this graph. You can see that they measure many different materials. The x-axis are the delta O18 value. And these are the count, okay, number of samples. The material here is anhydrous. This is the value of anhydrous olivine. So you see its value is around 5. This is also anhydrous. It is mantle material. The dating material is zircon. You see it's also around 5 to 6. They are 5 or 5 to 6. We skip this one. We just go directly to Jack Hills. This is Jack Hill. It is sandstone. And this is the O18 value of zircon found in the sandstone. You see its isotopic value is much more heavier than the mantle rock here or the anhydrous basaltic rock here. So this enrichment in O18 made scientists to propose that these oldest zircon, their presence indicate that at that time there was an active hydrological cycle, and that cycle includes liquid water because this kind of enrichment usually happens when there is sedimentary rock. So now I will conclude today's lecture with these 2 points. The Earth lost most of its hydrogen and helium. That's what we already said. But it efficiently traps water by the atmospheric thermal structure and plate tectonics. You know that beneath our feet in the solid Earth, there is another ocean. So this tells us where the water is and why the Earth is efficient at keeping water, liquid water. And then the second point is evidence from zircons indicates the presence of liquid water soon after the accretion of the Earth, as early as 4.4 billion years ago. So liquid water was present on Earth almost after it is formed. That's for today's lecture.